Hello class, welcome to the next segment in lecture 22, and this segment we're going to be talking a little bit about some composite parameters that are sometimes used in the severe weather forecasting process, and we're going to talk about what exactly they mean and some of the caveats that go along with them. So let's first start off with something that's probably of interest to most of us, and that is the significant tornado index, also sometimes referred to as the significant tornado parameter or STP. And the calculation for that is shown up on the screen here. And this basically just takes into account the combination of environmental factors that are typically associated with a heightened tornado risk. So, one of which is the mixed layer CAPE, which is basically a metric that measures how much buoyancy there is in the atmosphere. So, if you've got an unstable atmosphere, then you're much more likely to get robust updrafts and supercells are what you want to get in order to get tornadoes. And also, there's this term for the elliptic condensation level, which is sort of a rough estimate as to the height the clouds will be above ground level. And it turns out that if you've got cloud bases that are very low to the ground, you have less evaporative cooling of the rear flank downdraft, which means you're going to have warmer and moisture air in the updraft area still. And it's been shown that if you've got a warmer and moister downdraft or rear flank downdraft, then you have a better chance of getting a strong tornado. Versus if you've got very high cloud bases and you have a lot more evaporative cooling, you've got a much cooler rear flank downdraft, so you're going to have less of a tornado risk. Now, it's entirely possible to get a rear flank downdraft that is not cold enough. You still need to set up a temperature contrast in order to get a tornado to form. And if you don't get any temperature contrast at all, then you will get no tornado. And that's pretty universally accepted. There has been some recent research that might suggest otherwise, but ideally, right now it's widely believed that there is this ideal Goldilocks zone where you have a rear flank downdraft that's cold enough to generate some vorticity, some what's referred to as baroclinic vorticity, but also warm enough to support a significant tornado. And then another factor, again, this has been modified. This used to be effective storm relative helicity, but now the metric that we're using now is the surface to 500 meter storm relative helicity. And this basically assesses how much directional wind shear is present in a layer that's relevant to tornadoes. So tornadoes are phenomena that occur very close to the ground. So ideally, you want to look at how much directional wind shear is very close to the ground to assess the risk for tornadoes. And this value called effective bulk wind difference is basically a measure of vertical wind shear from the surface up to half the height of the storm. And this is again to assess the potential for supercells. So, are you going to have supercells, which again are the storm mode that is going to be most favorable for producing significant tornadoes? And then also this term over here, sin, which is how much the updrafts might be impeded. So, if you've got updrafts that are very impeded, then you're not going to have much in the way of robust updrafts, and you're not going to be having much in the way of tornadoes as a result. There's actually two different calculations for a significant tornado index. The other one is the fixed layer. So the effective layer is primarily used for storms that are in the process of forming. The fixed layer is primarily used for storms that are already formed. And the calculation is pretty similar. It's just some different metrics are used. So this uses surface-based CAPE instead of mixed layer CAPE, which again is just an assessment of how much buoyancy. And this uses surface-based elliptic condensation level instead of mixed layer. In a lot of cases, these are the same, but there are some cases where they're not. If you've got significant differences between effective and fixed layer, then you might have an environment that's maybe not as favorable for tornadoes. But if these two values are pretty close to each other, then usually there's not much cause for concern. Cause for concern in a relative sense. You might have to worry about tornadoes if these two indices are in fact pretty close to each other. And this still uses 0 to 1 kilometer storm relative helicity, but again, this is probably the better metric to use, the 0 to 500 meter storm relative helicity. And the 6BWD, that's basically surface to 6 kilometers shear, or the bulk wind difference between the surface wind and the wind at 6 kilometers. And then similar idea here, surface-based convective inhibition, which basically, again, quantifies how much the updrafts are going to be impeded. If you have updrafts that are fighting stable air, then they're not going to be as robust and may not be as long-lived. And another parameter that's widely used is the supercell composite parameter. So significant tornado index is primarily used to assess the potential for tornadoes, the potential tornado risk. And the supercell composite parameter is used to highlight an atmosphere that might be favorable for supercells. And usually values above 1 for the significant tornado index are a potential signal for tornadoes, and a similar thing for the supercell composite parameter. So here we're using most unstable CAPE, which is the most unstable convective available potential energy, which does not, basically by using MU CAPE, most unstable CAPE, you're basically saying that you don't need a thunderstorm to be surface-based. MU CAPE allows you to diagnose the potential for how much buoyancy might be present in a thunderstorm that's not surface-based, that's not drawing warm, moist air in from the ground level. So supercells don't have to be surface-based thunderstorms. If you want tornadoes, then they have to be surface-based. But if they're not surface-based, you can still get a thunderstorm that is supercellular in nature. So that's why most unstable CAPE is used as opposed to surface-based CAPE or mixed layer CAPE, which are for surface-based thunderstorms. MU CAPE is primarily used to diagnose the buoyancy of an elevated thunderstorm. And effective storm relative helicity is sort of what we talked about in a previous segment. And then same value up here, effective bulk wind difference, which again is the wind shear between the surface wind and the wind at half the storm height. And then again, another term that assesses how much the updrafts are going to be impeded. So these two parameters are pretty commonly used when looking at severe weather events. One to assess the potential for tornadoes and the other to assess the potential for supercells. Although there's a few things that I want to go ahead and mention about these parameters, first of which relates to significant tornado parameter, or STP. Usually, this is something I said earlier, but usually values over 1 can signal an environment that is favorable for tornadoes. While it is true that higher significant tornado parameter values are correlated with more intense tornadoes, it is very important to keep in mind that a high value of significant tornado index is not going to guarantee a major severe weather event. And this is something that comes up every spring. You see people, especially storm chasers, on social media posting, "Look at the massive STP values. This is going to be a big day, y'all." And then it turns out to be nothing, or not as big as maybe they were hoping. So there's a lot of things that are actually ignored by the significant tornado index, and we're going to actually go ahead and discuss those. Again, just because you get a high value of significant tornado index, it doesn't guarantee you're going to have a big severe weather day. There are other factors that significant tornado index doesn't account for that can also influence the potential for tornadoes. Perhaps the most notable of which is, will storms be linear or isolated? Significant tornado index does not account for the potential for linear or isolated storms. Of course, if you have isolated storms, you have a better chance of getting supercells, and you thereby have a better chance of getting more intense long-track tornadoes. But significant tornado index cannot tell you anything about whether storms will be linear or isolated. Too many storms. It is possible that too many storms go up in the environment, and if that occurs, then you have storms that are fighting with each other for warm, moist air. They're competing with each other, and if that turns out to be the case, then their storms are going to be perhaps not as intense as what they might otherwise be, and if they're not as intense, then they might not be producing very much in the way of tornadoes. But also, if you have too many storms forming, that could also favor a transition towards linear storm modes. Again, you can get tornadoes. You can get tornadoes out of linear modes, linear storms. But if you want a big significant tornado event, ideally you want isolated thunderstorms. Also, features that can impede the updraft. So we talked about convective inhibition, which is usually something that occurs near ground level. But you can also have features that can impede updrafts that are occurring well above ground level, such as sinking motions in the mid-levels or in the jet stream layer, which can produce regions of relatively stable air, which can either prevent thunderstorms from going up at all or can weaken thunderstorms that do go up. Another thing that's very important and also overlooked by the significant tornado index is this does not account for any potential weaknesses in the hodograph. So you can have hodographs that are, say, S-shaped, which give you messy storm modes. You can have S-shaped hodographs that give you high values of helicity, but those S-shaped hodographs are going to favor messy storm modes, which have less of a chance of producing tornadoes. And this is also a very big one. Could less organized thunderstorms form at an earlier time and eat up all the energy that was present in the atmosphere? And a slang term for this is, in fact, crapvection. It's probably a term that you've encountered at some point if you read any severe weather discussions or any blog posts about severe weather. But this is basically a term that refers to thunderstorms that go up really early in the day. They eat up all the energy, and there's no energy left for any supercells later on in the day when you might have supercell when the wind profile becomes favorable for supercells. And that's again another factor that's not accounted for in the significant tornado index. So again, just to reemphasize this because it is so important, just because you see a screaming high value of significant tornado index, that doesn't mean you're going to get a big severe weather day. It can be a signal that a big severe weather day is a possibility, but it's not going to guarantee that's going to happen. But that's going to do it on this segment for composite parameters. And in the next segment, we're going to actually look at some of the weaknesses that are overlooked by the significant tornado index, just to sort of illustrate the point that I've been making. So with that, I will see you all in the next segment.